moment, I want to go real basic and talk about nuclear spins. So, how can we control and how do we think about nuclear spins? I would say traditionally, and still the major paradigm is nuclear magnetic resonance, right? Have some nuclear spins, have a Zeeman Hamiltonian with a static magnetic field, and we have an oscillating magnetic field to perform nuclear magnetic resonance. And that is how we control these spins. Of course, this is everywhere, right? Like this is probably one of the most important discoveries in condensed matter from the 50s, that you use nuclear magnetic resonance. It's literally in so many branches. And we use it also for quantum computing here and there. This one is not known so well, I would say. Nuclear quadrupole resonance. So, this approximation where we say that we have a little sphere with a spin only applies to nuclei that have a spin number 1/2. But of course in the periodic table there's also nuclei that have larger nuclear spins. They are typically, as you get more protons and neutrons in the nucleus, but even some of the small ones have already a spin that is not 1/2, but larger. Now, in that case, you need to go beyond this spherical approximation of the nucleus. In that case, you need to realize that the nucleus is actually, to first order or to lowest order, it is a sphere, but then we have a correction there, the first surviving correction term, which is the nuclear quadrupole moment. So what this means is that rather than being a perfect sphere, the nucleus can be a little bit potato-shaped. A little bit elongated along one of the axes. And this then, this is the quantum version of a classical multiple expansion, so of a charge. So this is the next surviving moment. And in principle, this game can also be continued. The next one that you would see is the octupole moment. And people have observed it, but it's the next higher order term, so it is even weaker. So this is the first order in the spin operator. Then we have the Zeeman term. But this nuclear quadrupole coupling, as it is called, this is an approximate. I will give you at some stage in the slides the full quadrupole Hamiltonian. It is more complex than this. But to first, if you approximate it in its simplest form, it looks like this. It is quadratic in the spin operator. So it is the next highest order, hence we get now a quadratic spin operator. And it doesn't exist for spins smaller than 1. So you need spin 1 or higher to have this term non-zero. What this means is that now the nucleus cares about its environment. It wants to have a preferred orientation with respect to the charges around it. So in this case, where we have a quadrupole charge sitting around it, it will align in this way. Okay? Now, we can do the same, basically, we can keep doing nuclear magnetic resonance, but now investigate this transition, because there's now two preferred charge states, right? This is the ground state, and when it's orientated like that, it is the excited state. So we have an additional transition now, with additional splitting in the system. So without the Zeeman effect there, it means that this system is now has a single splitting in it. So the system, because there's a square in here, you don't no longer care about the sign of the spin state. All right. Now, this process of investigating this additional quadrupole splitting in nuclei is known in literature, in the old literature, as nuclear quadrupole resonance. And it even has some applications. It's being used in the detection of drugs and explosives, because some of the elements in those compounds are rich in elements that have a nuclear quadrupole moment. So it's sort of a niche type of magnetic resonance that has some applications. All right, so the control and detection of the single nuclei. I already said something about it before the break. So we have this static magnetic field, then we can add an electron to it, we have the hyperfine interaction. And we can access the single nuclear spins via the electron spin. Okay? That is through electron spin resonance and nuclear magnetic resonance. Okay? Now, that game can be done. It has been done in a variety of systems. I think, and Vincent is very famous for it. It's the exact same principle behind it, I would say. You have an electronic spin hyperfine coupled to a nuclear spin. Then, of course, our system of choice is another great example, and yeah, that is pretty much, I think, the most promising routes that people are investigating at the moment. All right, now, how about electrical control of nuclear spins? Okay. For that, if you want to have electrical control, you need to somehow have an oscillating field that couples to your spin, induced by an electrical handle. And in these spins, these nuclear spins that only have Zeeman interaction, there is no direct electrical access. Instead, what we can do, we can electrically modulate the hyperfine interaction. So we can take one of the gates on the substrate, for example, shake the electron wave function, but do that resonantly, on resonance with the nuclear drive frequency, and that way we can also drive the nuclear spin. Okay? Now, that has been done for donors in silicon. In this paper, it has been shown it has been done in molecular magnets. It's been done at UNSW as well for these donors, so this is possible. But one thing to realize is that, yes, we use an electrical knob in the device to drive the spin now, not a magnetic control line, but it is an effective magnetic field that we use. Okay, so you can rewrite this and what is as an effective magnetic field, so it is still acting on the Zeeman interaction in a sense of the nuclear spin. This is still an effective magnetic drive. Oops. Turns out there is actually true electric control possible. And this was Bloembergen was one of the, I would say one of the founders really of, after Purcell, I think, discovered NMR, shortly after Bloembergen joined him, and this whole era of the late 40s, 50s, where they just really worked out NMR. Bloembergen was like the central figure in there. Anyway, he also invented pretty much the laser, I would say, the maser, so he's a very important experimentalist in our community. He's a Dutchman, so some chauvinism here. But he basically, after the war, it was such a terrible situation in the Netherlands that he went to America and never came back, basically. So he had his whole career in, at Harvard, I think it was. Anyway. All right, so he writes, and this is just a conference abstract of a conference of AAAS, that is the organization that is behind science as well. So this is conference abstract of his talk there. And then he proposes it. If a nucleus or a paramagnetic ion with spin greater than ½ occupies a site without inversion symmetry, so a bunch of conditions that we need to fulfill, an externally applied electric field will cause, in general, a change in the quadrupole coupling constant. Okay? So when you have a quadrupole coupling, Bloembergen, he proposes that you can modify this coupling with an electric field externally. And then he even, so this is in a static sense, and then if the electric field is varying at a frequency, so on resonance, then you can also do transitions. So he proposed this in 1961. Of course, we were completely ignorant of this, right, when we did our experiment. Like, we come from nano-electronic devices, this is 1961, we don't have that literature knowledge in our minds, right, so we found all this out afterwards. So this effect, it was researched a little bit in those years. It is called the linear quadrupole start effect. And the idea is that you have the Zeeman splitting, you have some quadrupole coupling in there with a spin larger than ½ and now you drive it resonantly with an electric field, And what this means is that you do something like this. Okay? And you are flipping the spin by resonantly modifying the particle interaction. And for me as an experimentalist, these are really heroic experiments, I think. They really took like a material that has many particle nuclei in there. I think it was gallium arsenide. They put some capacitor plates on it and then hooked it up to like 100 batteries or something like that, 2 wires on it, and applied a big voltage across it. And they could see that some of these transitions, when they did the NMR experiments, they could see that these transitions were shifting. And then they also did it dynamically, where they applied a time-varying electric field, and they could see, this is all bulk. So you look at an ensemble and you look at the decay in an NMR coil. This is classic NMR experiments. And they could see this decay happening. So already in 1964, basically this was understood and done in bulk. And yeah, we just didn't know any of that. It's a weak effect. It's like 1 megavolt per meter gives you 5 kilohertz shift. I will show you a little bit later in the talk what that means in terms of our devices. All right, that is what I want to give as historic background. Now let's look at the periodic table and the group 5 donors. Okay. This one is completely understood and controlled, I would say, 31 phosphorus. So of course it is tempting to look at these other donors that have large nuclear spins. Bismuth is quite interesting because it also has a very large hyperfine, so there is zero field splitting there. Anyway, for our purposes to operate it exactly the same way as we use the 31 phosphorus, it is most convenient not to have such a very large hyperfine, so we stick to 123 antimony. Another good thing is that the implantation of antimony is well understood and controlled. So, yeah, fairly arbitrary choice of us to focus on 123 antimony, but we optimized it in maximize the spin quantum number for the nucleus that we could get given some of these constraints. So that was the goal of my postdoc project, to think about nice projects that you could do with one of these nuclear spins and in parallel build one of these devices, get it to work. That was 2016 when I started. 8 years ago, time is flying. Now, from a schematic perspective, this is basically like phosphorus, but a bit more. So it's the exact same principle, like everything I told you before the break applies here as well. But rather than having only 2 nuclear spin levels, we have now 8 possible states, because it's a spin 7.5. So it's effectively a 16-dimensional Hilbert space. Here we have small splittings of the order of 5 to 10 megahertz. Here we have a very large splitting of the order of 30, 40 gigahertz. We operate this at about 1 Tesla. So same game when we do the readout. If we try to read out this nuclear spin, we need to load an electron on it. So we do that with a known spin species, electron spin down, and then we can start reading it out. So the way that works is you initialize spin down. So you are in this part of the manifold. You apply a conditional ESR pulse. These are all very well separated ESR frequencies, so it's easy to address this uniquely. You apply a pi pulse here, and you look for a tunnel event. If you measure one, you have projected the nucleus into this state, in the plus 7.5 state. If you don't measure something, you also gained information. You have namely projected the nucleus into the complement. Okay? So we can have some complex superposition in here, and by playing this game, we start doing a projective readout. And simply by repeating this for the next ESR frequency, and we go over this entire spectrum until we have a positive readout event, we have done a full projective single-shot readout of the nuclear spin. So it's really, I would say, in a sense, the same as phosphorus, just you need to apply more pulses. But full single-shot readout of the nuclear spin. Initialization, of course, you do it through readout as well, right? And then, yeah, later on I will show you that we can control this. So we set out, made one of the devices, exactly the same one of these devices that I showed you before, now only implanted with antimony, and we started working on it. And the way you do that is that you start scanning the ESR frequency around the value where you expect to find the first resonance, And indeed, we did find this first resonance here. So we can drive this one. Once you can drive this one, you start scanning for this transition. So this is at 40 gigahertz. Now you start scanning around 5 megahertz or so to basically see this transition disappeared because you're pulsing the spin to this level, the nuclear spin. And then you lose your electron spin resonance. So we did that, applying an NMR pulse. And we did that on the ionized donor, so no electron on it. And we found at about 8.5 megahertz, we found this transition. And then you can keep playing this game, like trying to slowly map out all the whole spectrum of all these transitions. And what we found was that we got stuck here. So we really didn't know what was going on here. I was the postdoc on that experiment. PhD student Sermon was measuring very hard. I was telling him for weeks, like, whatever, this is bullshit device, just warm up, it's not working, let's try another one. Until he had a good idea. So, how did that work? When you fix the drive strength, so you drive the nucleus at a fixed magnitude, the oscillating field, your radio frequencies map out the coupling element in the matrix that drives the transition. Okay, so when we are driving between eigenstates 7.5 and 5.5, we are coupling it via the Ix or the Iy operator, and we can simply look at the size. Basically, you're mapping out the absolute size of Ix. So that is the trend that you expect to observe up to an arbitrary scaling constant, right, set by the overall strength of your driving. So provided you can keep the drive constant, which is approximately the case, you can do this game. This is a powerful way to investigate what type of transition you have. What we found was that rather than following this trend, which is really the absolute size of the first of diagonal of Ix, for spin 7.5, we were observing this trend in the experiment. So it was going down, and this one, we put the dot at 0. At that point, we didn't know if it was fully 0 or not, but we didn't find it. So this is completely, and when you notice, like, this is spin resonance in a well-defined spin system, you notice something is going different than what you expect. So that was Sarah's idea, of course, and that was why I gave you the introduction about Bloomberg and all that. What if these transitions are not NMR? We are not modifying resonantly Usageand, but we are resonantly modifying the quadrupole interaction. What happens then? Because we have products in the Hamiltonian of spin operators, we know that Ix squared will not go you the first off diagonal, it will give you a second off diagonal non-zero. So you cannot drive between neighboring states in quantum number. So you need to have a product that involves the Iz. So then, on resonance, the functional form that you have for the matrix element that couples the two neighboring states, when you are doing a resonant modulation of quadrupole, it has this form. So Ix times Iz, Iz plus Iz times Ix. That one can couple two states that differ by one spin quantum number. So again, this is just a prefactor, and we are mapping out the absolute size of this matrix element. If you now overlay that with the data, you see that there's a perfect match. So this was for us the moment where we realized that we were not doing nuclear magnetic resonance, but we were doing something else, nuclear electric resonance, namely driving the quadrupole resonantly. Okay, and then indeed this matrix element cancels out. You can see that, so this is why you cannot drive this transition. And once we realized this, so that explains why we were getting stuck, why we couldn't continue. I think this is really cool because it's like this whole story where this was all known by the founders of magnetic resonance basically in the 50s, 60s, next 1961. Bloomberg knew this and expected it, predicted it, even observed it with experimental collaborators a few years later. And this got just lost in history of physics. Maybe you knew this mechanism, I don't know, like older people may know it, but we were completely oblivious of it. But of course it's a natural thing that could cause this. So this is the first time that we have done this now in a modern way, using a single spin, you doing it coherently, being able to do Rabi's, etc. on a single nuclear spin. Now, then a natural extension, of course, is that if you have these quadratic operators in your nuclear counterpole Hamiltonian, you will also get terms when you drive that are of this form, Ix or Iy squared. And those couple spin quantum numbers that differ by a value of 2. So you basically drive those transitions. Okay? Indeed, we could observe these, and then this was like within the imperfections of our experiment. This is like a perfect match. As an experimentalist, when you see this good a match, you're very happy, I would say. And that then also allows us to skip over this forbidden transition using the m equals delta m equals 1 transition. So this is how we could then map out the entire spectrum and also find these other resonant peaks. So this was all done. This mechanism is called nuclear electric resonance. This was all done on the ionized delta. Okay? So that is how we go to this side of the manifold. Of course, why were we not doing nuclear magnetic resonance? This is an experiment that we designed to do nuclear magnetic resonance. Right? And that was why we were stuck in this framework that we had to be doing NMR rather than something else. So this is how an ideal device looks like. This was how our device looked like after we took it out of the fridge and measured it. Imaged it, sorry. What you can see here is that at some point, we don't know exactly when, we blew up the microwave antenna. So this was a broken device, a malfunctioning device. And this was a super tricky failure mode that took us like weeks basically, or maybe 2 months or so to understand. Because what happens is that such a small short, such a small break in the antenna, at 40 gigahertz, where we want to do electron spin resonance, it still acts pretty much like a low enough impedance so that you can get some signal through. We were able to do electron spin resonance, the magnetic driving, at 40 gigahertz. It was behaving poorly. We sort of saw already there that it wasn't the way it should be. But it wasn't until we realized we were doing something electric to the nuclear spin that we had this idea that actually there must be a break in here, and at megahertz frequencies this acts just like a capacitor. So we are having an electric driving here, because this is 3, 4 orders of magnitude difference in frequency. But this was a super tricky failure mode that I think resulted in some beautiful physics. We would have discovered that at some stage anyway later on, but this was now we stumbled upon it in a broken device by chance. So this is one of the cases where we managed to spin a broken device into something very nice, I would say. Like most of the times we don't report on our broken devices, but here it was worth it. All right, now if that idea is correct, right, at that point we hadn't imaged the device yet, but if that idea is correct, we don't need this microwave antenna at all to drive a nuclear spin. We can just use one of the many gates that we have in the device and hook our signal generator up to that gate. So that is what we did. And then, of course, we could get beautiful Rabi's, etc., and all that also using this gate. Okay? So this is for one of the transitions. All right? So that confirmed that picture to us. Now I want to dive, in the remaining time, I want to dive a little bit into the microscopics behind this system. And for that, we need to look into the counterpole interaction. So this is the counterpole Hamiltonian in its full form. So this is a 3 by 3 matrix of all the products of the spin operators, and the defining quantity in there is the matrix of second partial derivatives of electric potential. So electric field gradient. So this is not it's not 9 independent variables. This is a conservative field, so you have 5 independent variables in this interaction. But it's a matrix term. You have all these products of spin operators in there. The point is that this term, this quantity, electric field gradient, is very sensitive to the microscopics of the device, right? Like, you look at the math, you do some simple estimations of gate potentials that you apply. You see that electric field gradients coming from those macroscopic electric fields are completely negligible. It's like 5 orders of magnitude or so, or 4 too small to cause any counterpole interaction. What causes this electric field gradient to be large is distortions of the lattice or the bonds right around the nucleus. Okay? So the main mechanism that we have in silicon in these devices are always strained. We cannot define that exactly. It's property of the device when you cool it down. You put metal on top and an oxide on top of silicon. You cool it down by 3 orders of magnitude. You get a strained device. It's a complex strain profile, but there is some strain. That breaks the TD symmetry of the lattice, and that is enough to get a non-zero counterpole, a non-zero electric field gradient at the site of this nucleus, meaning that the counterpole is no longer zero. So to a large extent, strain can explain our static counterpole splitting. And it is mainly the shear strain, so this type of strain where you bend the lattice in this, as you can see it in this picture. I cannot really indicate it with my hands very well, but rather shear strain than the other strain component that we have. All right? Now, so we did some estimations of there. We observed in experiment 68 kilohertz, static splitting. Yeah, you can do some strain modeling in COMSOL. I don't think it's all that accurate, but it is a good indication that you're on the right track, I would say. So you convert the strain that you get, taking into account thermal, the thermal contraction when you cool down, and you convert that into the counterpole splitting that you expect, and do that with realistic geometry. We can use these gates to sort of estimate with 10, 20 nanometer accuracy where our donor is located. You find that in the regime where the donor is supposed to be, indeed, this yellow region in the plot gives us something like 50 kilohertz counterpole splitting. Right? I wouldn't bet my life on the exact number, of course. Like this is within a factor of pi or whatever, accurate. It's not, it's an order of magnitude estimate. But in any case, like, that is, yeah, that is, I think, pretty legit. Then we looked into this linear counterpole Stark effect. So can we shift those lines? So while we are driving, observing the transitions, we are also applying a static voltage to one of the other gates. And indeed, what we observe is that all these various lines are shifting a little bit. Okay? So within static electric fields, we can tune the static counterpole interaction. You can collapse all these lines on top of each other because they scale with the quantum number, so you can go through that exercise, the change in the slope here. You can collapse all these on top of each other and fit it through, and what you observe is that the shift here is of the order 5 Hz per millivolt. So this is, we are literally looking here at an effect of maybe 100 Hz or so, 5 Hz per millivolt, changing the gate by a tiny bit of electric field, tiny bit of gate voltage. So this demonstrates, I'm sure, that without, we really need this very narrow line width that we get, the 1 10 Hz line width of the nucleus spins to be able to observe this effect. And that is, I think, really cool that you can, these nucleus spins are so coherent that tiny effects caused by the microscopics around the nucleus can be resolved. So this scales linearly with the DC electric field, which fits into this picture. Now, the explanation for that is that, and here I think any of the estimates are very hand-wavy, it's not at best within an order of magnitude or so. But the idea is that when you have two different atomic species, chemically speaking, this bond is no longer symmetric. It's an asymmetric bond. And this causes a dipole moment here, and the electric field that you apply can couple to that. Okay, so by having non-symmetric bonds and applying an electric field, we can change the electric field gradient. So it really needs to happen at this level of the nucleus and its surrounding atoms to be of significance to the counterpole interaction. This is also, of course, this is also how the driving works, right? Like the static splitting happens when you affect terms along the quantization axis, and when you do it dynamically, you are affecting terms in the orthogonal plane to allow you for driving. It's all the same physical mechanism. Now, As a quick flash, basically, this was what we achieved during my time there, and then people, of course, continued the experiment. I was still a little bit involved with this experiment, just to show you that we by now have full control over the system. The one term that we didn't look at yet is the electrically modified hyperfine interaction that gives you electric dipole spin resonance, EDSR. But otherwise, we have discussed all these terms already. And the point is that you have all these transitions in this manifold, in this Hilbert space, right? We have ESR, electron spin resonance, that are the direct horizontal ones. We have EDSR that allow us to do flip-flops between the nucleus and the electron spin. So we can go diagonal in this direction. We have full control over the nucleus through magnetic resonance and electric resonance. Okay? And both in the neutral and in the ionized case. All right, and then here you see all the spectra. So this is an ESR spectrum for the full donor, an EDSR spectrum. Here we have the ionized NMR spectrum, the neutral NMR spectrum. So we can completely map out this system now. We can, of course, the NERs are not shown on this slide, the electric resonance, but they are, it's possible as well in this device. In the first device that I was studying, because of the broken antenna, we couldn't get all the various transitions, of course. So from this we can deduce some of the parameters. We have a hyperfine interaction around 100 megahertz. It's slightly deviating from the bulk value of antimony in silicon, and that's probably because some distortions of the wave function. We have a quadrupole splitting. This is another device, so the value is slightly different. For the ionized donor of about 40 kilohertz and about 50 kilohertz for the neutral donor. So this indicates like the quadrupole splitting is highly dependent on the device. Okay, so this depends on the local strain conditions. Yeah, so here we show full Hilbert space magnetic control. So this is ESR radio oscillations, and here neutral nuclear NMR. So full control this way, and here we show full electric control. So this is EDSR, so electrically by driving those transitions, and here we show you the ionized NER. Okay, it is, I think, quite neat that we can in principle address this system entirely electrically. There's no real need anymore for a magnetic antenna. All right. In terms of coherence, these drive mechanisms are the same. So this is for the ionized nucleus, one of the transitions, and NER and NMR basically result in the same Ramses. So really we find the same T2 star. And perhaps the last interesting thing to look at is how the T2 star depends on the nuclear state you are in. And the reason why this is interesting is that, of course, we have introduced a new interaction term into the system, an electric one. So this nuclear spin should now be somewhat sensitive to electric dephasing mechanisms. And there's not much data yet. We have measured this by now on 2 of these nuclear spins, so maybe 3 by now. But it does look like there is a trend there, namely that the central one transition has the highest coherence, and the outer ones progressively go a little bit worse. And the reason for that is that the central one, that is the transition you cannot drive directly electrically, so it's insensitive to electric noise. And as you go out in the spectrum to these other transitions, the contribution of the electric noise basically increases as well. So we somewhat observe this trend. All right, that was the last thing I wanted to show you. I think of course, experimental progress is much slower always in your in real life than in your mind. I hope to be at this point during my postdoc, and it's only happened last year. The point of today really is that we can do all this, that we can have these high spin nuclei, have full control over it, magnetic, electric, exquisite control, I would say. Line widths are extremely narrow. We can look at really subtle microscopic effects. And in the next lecture, basically the final one, I want to basically give you snapshots of all the various things that we plan on doing with this. and possible extensions, etc. of this system. Yeah, but this is the model system, or the system that we work with. That was it for today. Questions? It's not it for today for me. It was on record. Any questions? Personally speaking, I'm just amazed that you can do all this with one of these nuclei. And this is very messy condensed matter solid state device, right? Like coming out of our clean room. But we work on this very clean silicon lattice, and because it's a single defect, you can actually fully understand what's going on and look at very subtle effects. I find that very neat. Because I did my PhD on quantum transport, right? Like it's a very different ball game, I would say. Also very nice and interesting. Yep.
Is there like a charge noise, or which sources of noise?
I would say you can take noise spectra on these nuclear spins, but it's very tedious because they are so slow, so it takes very long. But you can in principle do it. You do dynamical coupling, decoupling, and then you do that as a function of the number of pulses. You can say something about the noise sources, or at least the spectrum, and then you can try to link that to possible noise sources. Reality is, of course, that this is a nano device. We are working just below the interface, 10 to 50 nanometers or so. So we have interface traps between silicon, silicon oxide, charge noise on the gates, etc. That may affect things a little bit. So we can be certain there is charge noise. But exactly what affects what source affects what property of the system, pretty difficult, I would say, to disentangle. For the phosphorus, for the electron spin, it's a bit easier because it's a faster system. But I must admit that I don't think it resulted in all that much insight into what is the limiting factor. But what can I say? Also for the electron spin, the T2 stars are pretty good. The real issue I see with the entire platform is what we discussed in the break, like scalability is very difficult to achieve. At the level of 1, 2, 3 of these donors, a lot is possible. That is why I think it's so cool to have spin 7.5, because you have 2 or 3 of them. You have a gigantic Hilbert space to play with. Right? It's very slow and tedious because of that. The absolute time scales in human lifetime are very long. But it is all possible. And this is for sure, like, you just fabricate enough devices, you will get 2 of these donors coupled to each other. You can work with 2 nuclear spins. That's like 8 times 8 Hilbert space nuclear. Some 1 or 2 electrons in you grow very rapidly. Yeah. And then because they are so coherent, you can also start looking at very subtle effects in the dynamics of these nuclear spins. But I think it would be unfair to claim that you can build a quantum computer out of this. Then we need breakthroughs in terms of device development. But solid state systems like this, working with spins of complexity, Hilbert space of 8, Hilbert space of 2 times the tensor product 8, that's pretty significant. Like, normal spin qubits, electron spin qubits cannot do that yet. From a fundamental viewpoint, it's also really cool that it's a single degree of freedom that has this large Hilbert space. Okay, I'm sure that theoreticians will, the first thing theoreticians ask me always, like, can you sweep the spin quantum number in experiment? Like, can you adjust the spin quantum number? And it's like a natural question for them, because they want to go from the limit of spin 1/2 to spin 1000 and see how, for example, dynamics changes if you go to more classical like spins. But yeah, unfortunately, that's not how it works. We have 3 or 4 or 5 possibilities, all between 3/2 and 9/2. Yeah. Anyway, I'm talking into your break.